seeing a reflection here which is glaring a bit. Can I wear anti-glare glasses or something? Might help. I have to do something. I'm worried. Right. So rules like this, they consist of, on the left-hand side, just a single variable, as they all do, because it's a context-free grammar. But on the right-hand side is another single, just one variable. Rules of this form are called unit rules, because you only have one variable on the right-hand side. You have one and only, well, there's only one symbol, and that symbol is a variable on the right-hand side. So rules of this form are called unit rules. You also throw those out. Now, why? Well, the general strategy is throw out rules that do not conform to CNF. They're not of the Chomsky normal form. In other words, if you have two variables like this, and only two, that's okay. Don't do anything with them. They're fine. They're already okay, right? But if you have unit rules like this, throw them out, and then you'll have to repair. You'll be adding other rules. We'll go into detail in the detail proof. The full proof after. This is just an overview, right? The proof idea. Okay, so you repair the grammar. You add other rules to the grammar. This is the new grammar that you're generating. That will be in CNF, Chomsky normal form. Okay, so that it still generates the same language. In other words, it's equivalent. The new grammar you're generating is equivalent to the older one that you start with, and the new one will be in CNF. Okay. Okay. Once you've thrown out the unit rules, then step 4 would the remaining rules. For example, you might have on the right-hand side, you might have like 3 variables or 4 variables, and so on. So you'll see when we get it, well, it'll be next session. You'll see how to convert those rules, and you'll have to add several probably. Usually, you'll add several new rules that are equivalent to the rules that remain, and typically they will have. Well, they won't have 2. That's okay. You won't touch those. Those that have 2 variables, they're already in CNF. So you'll be dealing with rules that on the right-hand side have maybe 3, 4, 5 variables in them. Okay. All right. So that's the overview. It's a little bit vague, but you've got some idea of the picture. Basically, throw out rules that do not conform to the CNF, the normal form, and repair the damage by adding other rules that make the new grammar that you're constructing equivalent to the old grammar. In other words, it generates the same language. It generates the same strings in the language. All right. So now, so now the proof. We'll do the 4 steps. So the very first one was you just add a new start variable, okay, and we'll call it S0, okay, and a rule. So you're adding a start variable to your V, the set of variables, and you're adding a new start. Well, it's a start rule here. You're adding this to your big R, the set of substitution rules. Okay, so add a variable and add this rule. Now what's that? A couple of comments here. What is S here? That's the start variable of the old grammar that you started with, right? So that's the start variable of your new grammar that you're constructing. That will be of CNF. It will be of Chomsky normal form. And that S is the start variable of the grammar you started with, the grammar that you are converting, okay, the original one. All right, now why do that? Well, because by creating a new variable, S0 here, this variable here will not be in any of the rules, other than this one, on the right hand side of those rules in the old grammar. Okay? By doing this you ensure that this new starting variable only occurs once in your new grammar. Okay? Because and you just connect it to your starting variable in your old grammar, the one you're starting with. Now, in your old grammar, this s may also appear in the right hand side, perhaps, of some one or more of the rules. Okay? Now, to avoid that situation, you do this. You create this new variable s0. Right? That's what it says here. Okay? So this ensures the new start variable, this one here, does not occur on the right hand side of a rule of your original grammar G. Okay. Okay. Now, second step. Now, a bit of a reminder. What was from the proof idea? What was the second step? You eliminate rules of the form variable arrow epsilon. So variable arrow empty string. You may be asked, why do you do this? Why, for step 2, why do you eliminate a arrow epsilon? That's harder to answer. I guess the obvious answer is, the simple answer is, you will see why with experience when you come to do this kind of thing for homeworks in the problem solving session. And there are, I think, 35, I think we looked last time, right? It was, I think, 35, is that right? Or 45, hold on. How many questions? 45 questions. And this chapter is only 30 pages. Now, there were 65 questions in the previous chapter, but that was 50 pages. So proportionally, there are more questions in this chapter than the previous one. Right? So when the time comes for you to get into the nitty-gritty of problem solving, these rules, these techniques will gel. They will crystallize, and you'll see the point of why it's done. It works. Well, that's what I'll say for the moment. Alright. Okay, so step 2 is you eliminate rules of this form. Okay? So a arrow epsilon, the empty string. You throw these rules out from your original grammar G, and then we'll have to repair the damage. We'll explain a bit later how that's done. Alright, now the variable that's on the left hand side, that's not to be a start. That's not to be S. Now remember, S is the start variable of the old grammar of your G. Okay? So you don't throw out something of the form, I guess, big S arrow E epsilon. Okay, now you throw this out. Now for each time, you look at your rules in G, your old grammar, you look at the right hand side of them, and if you see an occurrence of A, where A is on the left hand side of a rule like this, an epsilon type rule, okay, if you see that an occurrence of A in the right hand side of some rule, then each time that A occurs, you write out a new rule, and you throw out the A, the symbol A, in that rule. So if you have, for example, let's see, you may be able to see. Here's an example here. I think you can probably see this first line of the next session. So here's a rule, and let's say you had a rule that A arrow epsilon. And here's a rule with A's in it in the right hand side of a rule. So you will add you'll throw out the A arrow epsilon, you throw that out, and then you'll add 3 more rules to your rule set that would correspond to eliminating this A, so you'd then have UVAW. The second one, you eliminate this A, so then you'd have UAVW. And the third possibility is you eliminate both of them. So you just have UVW. And you may ask, well, why do you do that? Same answer as before. You'll see why it works just by doing it. You've been given a recipe now, an algorithm with quite a few details. You need to study this quite carefully, especially if you're going to use it later for the problem-solving session. All right. So I hope that's clear what you do. Maybe you're not too clear yet on the why you do it, but that's another question. Right. So let's see. Okay. So you're looking for these epsilon type rules. So A arrow epsilon. If you have a rule like that in your rule set in G, in your original grammar, throw it out, and then go looking for this A. Whatever this is, whatever variable this is, might be B, C, W, whatever. In the right-hand side of the other rules. We're just generalizing here, we could just call it A. Now say you find a rule like this, right? So you will you'll replace the A by, well, you won't, you just throw it out. So you'll add a new rule into your rule set, and in this case it'll just be UV, R arrow UV. Okay? When you have more than one A in the right hand side, things get a bit more complicated, and you do what I was doing just a bit before. All right. So you'd add this rule. You throw out the A here, and you add that rule to your rule set, and you do that for each occurrence of the A in the right hand side. Now, if you have more than one, well, I suppose you could generalize. Let's see. Well, actually, I'm not too sure. If you had like 4 occurrences, well, let's say 3 occurrences of A, would that mean you have 4 new rules, or is it more complex than that? I'm not sure. Sipser doesn't say. All right. So here, he explains what happens when you have 2 occurrences of A. What happens if you have 3? Like, can you eliminate 2 of the 3? I mean, then you start getting all kinds of combinatorial type problems. So I'm not sure about that. I'm not enough of an expert in this in CNF to be able to answer that question for you, I'm afraid. Right. Well, that's the end of that session.